Thanks for the introduction. Yes, so this is hopefully going to be a light talk. There'll be no proofs, and that's the first. But anyway, so it's going to be a light talk. So please ask a lot of questions and so on. It's mostly going to be setting up the problem because it's sort of like one way to model the problem I'm going to be presenting. Triangular Dvoretzky matrices are going to come up as one kind of solution, but there might be other solutions. So part of the point of the talk is to see if people come with other things. Okay, so let me start with this notion of distortion. So it's a fundamental, quite natural notion in geometry. So let's say I have a subspace V in R to the M, and R to the M equipped with the L1 norm, let's say. So then I say that this subspace has distortion delta if, when I look at the scaled ratio between 2 and 1 norms of any vector in the subspace, then that scaled ratio lies between 1 and delta. Now, what is special about this is that, I mean, if I had no restrictions at all, this delta can be as large as square root m, right? Because, so certainly square root m times the L2 norm is always bigger than the L1, bigger than or equal to the L1 norm. So that part is tight, right? This is achieved for, I mean, let's say if you take the all ones vector, and on the other side though, if you take a standard unit vector, this ratio can be as high as square root m. So these are special subspaces. So we want to look for special subspaces where the right hand side cannot go as far as root m. It's bounded above by some constant. So the question is if such subspaces exist and how large are they? So Dvoretzky theorems are a statement that such subspaces exist in quite a bit of generality, not just in L2, L1, but in other when you're looking at other pairs of norms as well. In particular, so in the special case of L1 and L2, what the theorem says is the following: that you fix a distortion at some constant bigger than 1. So essentially there's a constant fraction smaller subspace which will have that distortion that is no worse than delta. So this is saying that so you'll have, so there will be a subspace V of dimension at least n. So you'll have some k which depends upon delta, such that in R to the kn there will be a subspace V of dimension at least n which has distortion at most delta. So it's saying that there are large subspaces which have small distortion. So and Dvoretzky theorems are general statements of this form for arbitrary norms, but we will be looking only on L1 versus L2. Okay. Another way of writing down this this theorem is, it might not be immediately apparent, but it's not that far off from this, is to say that there is a k. Yeah, so C can be taken to be the same as this k. There's Cn cross n matrix A, which has the following property. It has this kind of a condition number property, that its 2 norm multiplied by the 1 to 2 norm of its inverse, that product is not too big. And how, in fact, exactly how big is the distortion divided by the square root of the dimension of the full space. These two statements are equivalent. The point is that you just, so if you have this, then you can just take the matrix A to be the rotation that rotates you into V. So it takes some n-dimensional subspace of Rn and just rotates it into V. That would be the matrix A. And if you have such a matrix A, then going to that is just to take the image of A. Okay. So what is the inverse here? So inversion is on the range of A. Yeah. So in this whole talk, whenever I talk about inverse, we'll just understand it's on the range of A. So it's a Moore-Penrose pseudo-inverse. Okay. So all of this is very geometric and very classical. So the list of references here, it starts with the work of Dvoretzky and then Millman. Then measure concentration came into this field via these 3 papers, in fact, and then there are lots of work on this. So the reason the measure concentration ideas come in and is because one way to prove this theorem is to just take a random subspace or a random matrix, an appropriate random matrix, and you prove that has the right properties that you want. Okay, so this is the classical interpretation of the Dvoretzky theorem and associated results. One can also interpret it in a coding theory or information theoretic setting. So let's look at that briefly. So in this setting, we have a message. We think of it as a vector in R to the n. And so our messages are going to be real numbers. So it's not the traditional finite alphabet coding theory, but over reals. So, and our encoding is going to be just multiplying this vector by this matrix A. And this matrix is the same matrix that came up in the Dvoretzky theorem. Okay. And we'll require, so one thing that one might require in a coding theoretic setting is that this matrix be of norm 1. And the reason, the interpretation in this setting is that this encoding process should not increase the power of the signal. So this, the mean squared, so if you just square the signal and sum it, that has not changed. That cannot increase in this encoding process if the matrix has this property. So that's the encoding. And then you send this over some channel. And on this channel, the adversary is allowed to add some noise. So you send this Z0, but what is actually received is Z0 plus Y, where Y is the noise. And that you have no control over. It's not random noise. Think of it as adversarial noise. And then on the other side, we have to somehow decode. So we want to find out get something close to this X. So, so in this setting, what we would do is we would try to find, so this Y can throw the, I mean, of course, it will in general throw Z outside the subspace, which is the range of A. So you just project it back to that range and then invert A on that. So that's all very good. What's it good for? The point is that the Dvoretzky theorem is essentially this statement that this whole process has the following decoding guarantee: that this X prime that you decode is close in Euclidean distance to the actual X. And how close? It's of course the higher the noise, the higher the error. But whatever that noise was, it's scaled down by the dimension, and up to a factor, which is the distortion. Okay, and the notion of a rate. So another thing in the coding theoretic interpretation is the notion of the rate. Sorry, so C and K are the same again. And the notion of the rate is this K. So the point is that you might expect, of course, that if the larger the space in which I'm allowed to embed my message, the better I should be able to do. So what the Dvoretzky theorem says is that with constant rate, in the sense that you only need to increase the size of the message by a constant in terms of the dimensions, and still you can achieve this guarantee, which that whatever the noise is, that is scaled down by about square root n, where n is the total length of the message times the distortion. So it's another equivalent way of stating the Dvoretzky theorem. So, so any questions about any of the three? No, so these are related quantities. So as I said, so what C you can choose depends upon what delta you choose. So you fix a delta and you get a C for that.
That's right.
Yeah. Yeah, so that has been optimized. So that's not, yeah, so people have tried to optimize that a lot, and I don't know if the best constants are known, but yeah, things should be close to what's best. So that's not going to be the focus. For us, it's just going to sufficient that this C is a constant. So take delta constant, then there's a constant C which works. Yeah. So yeah. So that's a good question. So so one construction is just a random matrix works. So you just take with very high probability. Yeah. So if you choose, so essentially the proof will go like this: that you will if you choose C large enough, then the probability that it works it increases exponentially. So the probability are exponentially small in n that it doesn't work.
So when constructing
Constructing a good this. Yeah. Yes. So that is in fact one of the, so one whole area works is to just come up with constructions of this A which are not random, or use fewer random bits. So that's something that I won't go into, but that people have worked on that as well. So like suppose that so you want first of all to keep C small. You also don't want to use too much randomness. You just want a deterministic construction that tells you which entries should go where. So this the usual construction will require n squared random bits, or order n squared, because each entry is random. There are constructions which can get it down to sublinear, n to the delta, where delta is less than 1. So the Dvoretzky theorem, of course, is that exists for all. I mean, so that's a statement that. So that the statement there is that inside any Banach space there is a Euclidean subspace of large enough dimension. So all LPs are also there. Yeah. So what exactly? So how big? So this particular thing about just having a linear sized subspace. That is true only in L1, L2. I think in general it can be logarithmic, so it can be much smaller. But yeah, yeah. So in terms of the de-randomization, most of the results I'm familiar with are in the L1, L2 setting, and that's because of computer science applications. Because there is often cases when what you want to do is L1, but it's more efficient to do L2, and then these things are embeddings, and you have to understand the properties. Okay. So the question we are going to ask is the online version of this. So here, notice that you had the whole message with you in the beginning. So you had the message with you, and then you had this matrix A, and you applied A on X, and that's the thing you send on the channel. So that's the setting of so-called block coding in the language of coding theory, that you have the whole block message available to you, and you're encoding it as a block and sending it. So the whole message is available. So what we want to do is online coding. So so we want to look at a situation where you get coordinates to the message one at a time, and at each time you're now allowed to send some k that has to be similar, that is supposed to be similar to the previous k that we had, some constant number of real numbers on the channel, which can depend only upon what you have seen so far. It can depend upon the prefix of size t that you have seen so far. And you want, and yeah, so for our purposes, we'll still require our codes to be linear, in the sense that our code should still look like multiplication by a matrix. So then this condition essentially boils down to saying that now the encoding matrix must be a triangular matrix of this kind. So it looks like a staircase, essentially. So and this is k times t. So each of these staircases is what you get to multiply at the ith staircase is what you get to use at that ith time. And so essentially that's saying that you get to send k numbers at that time. Those k numbers are k linear functions of the t things that you have seen so far. Okay. And of course now we can't ask for the same kind of decoding guarantees that at each time t we have the strong property. But what we can ask for are the following two informal things. The first thing is that the error in decoding a particular coordinate, so fix one small time t, and then as time goes on, as time goes on, as capital T becomes bigger and bigger, much bigger compared to small t, then the error that you have in decoding that small t is the xt for that small t should go down to zero. Should go down to zero at a good rate, maybe at about 1 over capital T. And the second thing that one might want is that, so okay, of course we don't expect to be able to decode very recent entries, because the adversary might just be able to swamp those out completely by just putting a lot of noise there. And we might then have to wait for a while before we get more data about those last entries. But in the case where the adversary has not been introducing errors, so suppose the adversary has not swamped out the very last thing it was sent, then we also want the decoding guarantee for those even the recent entries to be good. So it's two things. So one is that no matter what the adversary does, we want the decoding guarantee for things in the very far past to be good, because we have had a lot of opportunity to communicate data about them. And secondly, in case the adversary is acting nice and has not introduced errors in the recent past, then the error in decoding those also should be small. So the way we will do this is by encoding these two requirements into two separate norms, a scaled L1 norm and a scaled L2 norm, and then ask for decoding guarantees in terms of those. So for the first one, I'll just call the star norm. So what we'll ask for is that instead of the L2 norm being less than about square root t times the L1 norm of the noise or the error, we want this star norm, it's a time-weighted L2 norm, to be smaller. And this weight is just what that says. So you put higher and higher weight, or rather you put very small weights on the recent entries, and you put weights that are very similar to what L2 norm would put, like 1, as for things in the far past. So that's what this is doing. So for entry, yes, so the adversaries thing can be arbitrary here. So in the end, your guarantee has to be of this form, that whatever the adversary put in, your error should depend upon the norm of whatever the adversary put in. How that was computed is completely up to. Okay, so we'll ask for decoding guarantees in this sort of with this kind of a metric, that it's an L2 norm, except that entries that are very recent are weighed down. So we don't care about making errors on the recent entries. Any questions of this? And for the second one, so what we can do here is that so similar to that, we can now try to weight so instead of measuring the adversaries output by just the L1 norm, we can try to weigh it in such a way that we put a higher weight on errors that were introduced in the past. So errors that were introduced in the far past are given a higher weight, so that in your decoding guarantee, you have to ensure that those contribute less. So errors that were introduced in the far past have to be removed as time goes on. And we will not want both, we will not want one of these at a time, we'll want both. So it turns out to be easier to have slightly more generalized versions of these, where instead of just having these weights of this kind, we have a parameter mu, and we say that the star norm with mu is just the same weight raised to the power mu, and the dagger norm, so which was this here, is the same. So the dagger norm with mu is just that weight with 1 minus mu. So the reason for mu and 1 minus mu is not just a choice of notation. Actually, one cannot do better than that. So given that if you fix mu, the best thing you can do here is 1 minus mu. So one can show that something of that kind. And I won't go into that. But given mu, this choice of 1 minus mu is more or less forced if you want to do anything interesting. No, so yeah, so there are two things. So you can try to increase it or decrease it. So instead of 1 minus mu, try to have something larger or smaller. One side, so smaller would give you worse guarantees, and larger are just not possible. So this is in that sense. Okay. So the main theorem looks like this. So you fix this parameter mu, which is in these norms, and then there's another parameter delta. So I'll come to what that is, and that determines the rate k. So what this k has to be, and a constant c0. We'll come to that. So that the following is true. So there is a k times capital T cross capital T matrix. See the encoding matrix, which satisfies the following two conditions, the conditions that we wanted for all of the for all times t. So at all time small t up till large time capital T, you have the power constraint, which means that the total power of the signal that you transmit up till any time small t is no more than the power of the signal that was actually received up till that time t. So this 2 to 2 norm of CT. CT is just the K T cross T principal submatrix, the leading principal submatrix of C. So it's just at a given T, it's just this. And the second guarantee, which is of course the more interesting, is it might look slightly different, but this is what gets you the decoding guarantee. It says that if I take any vector x of the dimension small t and apply CT to it and look at its dagger mu norm, then that is at least up to this loss of t to the delta is at least square root t times the star norm of x. So this is in some sense a statement that the inverse, the 1 to 2 norm of the inverse is small. Yeah, so let me just do this proof that this is, yes, it's a small proof that this implies this following decoding guarantee that so I'll show what the decoding algorithm is. The same decoding algorithm that I showed you earlier. If you decode it like that, then if x0 was what you sent and the encoding is ct of x, then at any time t, the thing that you decode x tilde is in the star norm at most this far. So whatever the noise introduced was, if you measure it in the dagger norm, then the error is attenuated by this essentially the same kind of square root t factor. There's a t to the delta loss, but apart from that, it's the same kind of situation that was. So it's the same kind of guarantee that you had here. So here it was like root n was the total number of coordinates transmitted. And here it's root t except for this t to the delta. So I'll say a bit more about the t to the delta, but let's just recall once more how this was derived and how that decoding guarantee implies this. So it's pretty simple. So yeah, so the decoding is again, yeah, so the decoding is again the same. So yeah, so again the message is, so yeah, so this is at time t, right? So this is at time small t. So we're looking at one fixed time small t, and we want to say that at that time t we have this guarantee. And the encoded message, let's call that z0 as before, is ct times x0. Then there's of course some noise. So received message is z, which is plus y. Y is the error. And now, so the decoding is again going to be similar to. So we'll first find z prime, which is instead of finding the argmin with respect to the one norm, now that we are measuring errors in this dagger norm, we just have to do that minimization in the dagger norm, and for all vectors in the range of CT. Okay, and then finally, yeah. So and this x tilde would be, and CT inverse is now well defined because you're in the range. So let's just see that this guarantee is achieved. Okay, so what's up? So the point is that because z prime is in because z prime is in the range of CT, it is equal to yeah. So z prime is equal to CT of x tilde. Just by definition. So right. So so now we know that we know two things. So we know that the dagger norm is bigger than c dot times t to the half minus delta times the star norm of x tilde minus x0. So why is this? So this is just applying the theorem. So that's precisely what the decoding guarantee says. So this is something we have, right? Now, why does why is that sufficient? So now we have so we want to say that this is small, right? So or we have to show that this we have to somehow relate to y to the dagger norm of y, right? Which is so to the dagger norm of z. So this is really y, right? Well, it's not really y, but yeah. So this somehow this thing z prime minus z is what we have to relate to y, and now I claim that this. So of course, so this is so this is really z prime minus z naught, right? So this I claim is at most 2 times the norm of y, and that is because of this argument. So what is happening? So here is the range of, this is the range of CT. This is the subspace which is the range of CT. What has happened is that Z0, so Z0 is a point in it, because Z0 is by definition in the range. Then the Z is not a point in it, because there's some Y that was added onto it, and in general it won't be. So this is Y, and this is Z. But now what do? We find Z prime, which is the closest point to Z in the range. So, I mean, of course, it's not a L2 projection, but that picture is correct. Okay, so this is Z prime. So we project Z back to the subspace in this weighted L1 sense, but what does that tell us? So how far? So how big can this distance be? Well, I mean, so the point is that Z minus Z prime has to be less than the norm of Y. So this is the main observation. And this is clear from this because I drew the picture like that. But the point is that Z0 is a point in the range which is at distance at most this to Z, and Z prime is the closest point in the range to Z. So its distance better be less than Y, because we have one point which is distance that much. And that is it, because now Z prime minus Z0, this distance is at most by triangular inequality this plus this. Both of them are less than equal to this. One of them is equal, one of them is less than or equal to. So you get twice. So that's where this factor of 2 comes from. And that's so just to complete the thing. So what you have shown is that this is bigger than twice. So it's a fairly simple thing. It's just a repetition of the previous thing that I showed you. Okay. This 2. And then so this chain of inequalities is precisely that guarantee. Less than or equal. This is. Let's find it. So I want that this has to be. This is less than this, right? And wait, what am I saying? Z prime minus Z0 is less than, right? This is not less. And so then you just take this chain, just move this to that direction, you get this. Okay. So decoding is not complicated. I mean, at least to describe it is not complicated. Of course, hidden inside this computation is a linear program, right? Because you have to do L1 optimization, so it's a linear program. But apart from that, it's exactly the same decoding as before. And it gets you this guarantee.
Did you say maybe I
Yeah.
The standard case, the non-triangular case,
Mm-hmm.
the proof technique is using the probabilistic method. So
yeah, yes. One way to prove it is the probabilistic method.
And here as well?
Yeah, here also it will be a probabilistic.
So the construction of city is also by.
Yes, so that's the next thing that I'm going to do. Yeah. Okay. Yeah. So yeah. So as Jose pointed out, so how do we construct the C? It's a random matrix, and but it has to be a slightly. It can't be a standard random matrix because first of all it has to be triangular, and then you have to have this power constraint as well. So. But before that, let me just say, so there's this loss delta here, which is not there in the traditional thing. We don't know if it's completely necessary, but we can show that you cannot have exactly t to the half there. At least a logarithmic loss is required. So I won't go into the proof of that, but if you have, essentially one can show that if you have the decoding guarantee, without the delta, then the power constraint cannot be satisfied. Except for unless you allow a log square root of log t loss. So we don't know if this delta kind of like super logarithmic loss is necessary, but at least a logarithmic loss over what is standard is needed. Okay, yeah. So that's the construction. So the proof for this, I'll just say a few words about it. So the proof goes by randomized construction. So it is a Gaussian random matrix, but you have to scale down the variances in an appropriate fashion. And so let's forget about this factor. This is just for some normalization. The point is that the variance depends upon how far you are from the diagonal. So things that are on the diagonal have variance almost 1, which is very far from the usual construction of Dvoretzky matrix. So the usual Dvoretzky construction would have like 1 over square root n variance everywhere. This one has variance very close to 1, but it goes down. When you're really far from the diagonal, if you're at distance k from the diagonal, distance L from the diagonal, then the variance has gone down to 1 over square root, or 1 over L. So I should have, just to repeat. In the usual Dvoretzky thing, you have the variance is 1 over n. The standard deviation is what is 1 over square root n. Here, the standard deviation is 1 when you are on the diagonal. As if you go far from the diagonal, you start behaving more and more like the usual Dvoretzky, usual standard Gaussian random matrix thing. And more precisely, the standard deviation is like 1 over square root L at distance L from the diagonal. And yeah, and this is just for normalization. So just to make sure that the power constraint, etc., is valid. These logarithmic factors are just for that. Yeah. So I won't do the full proof or even any big part of it. But let me say, so there are two parts to the theorem. So one was the power constraint and the decoding guarantee. The power constraint one proves by just appealing to standard results. And the point is that now you have these entries which have different variances. So you have to use results from results on expectations of the 2 to 2 norm of such matrices that you have variable variances. So the one that's closest to this is this one by Bendir and Von Handel. There are better versions of this more recently, like in the last 1 or 2 years. But this is sufficient for our thing, and that sort of more or less immediately settles this. That things behave exactly as you would want. It's slightly more complicated to look at the decoding guarantee. So this is basically trying to find out lower bounds on what this matrix M will do to a vector in terms of the dagger norm. So first thing is to remove the dagger norm and to go to a usual matrix. So you just rescale the entries of M slightly, and then you're back into analyzing some other matrix which has slightly different entries of this kind. but you're now back to analyzing L1 and L2 norms. And the way the proof goes, and this is more or less all I'm going to say about it, is the following. So this matrix, this M or B, they look like this triangular matrices. What you do is you do this kind of an inductive argument with like sort of exponentially increasing scales in the following way. So at the jth scale, what you're doing is, so here's a big matrix. You look at this part of it, which is like a part close to the diagonal of like about half the size of the matrix. Inductively, you know that somehow behaves well in some way. And what you show is that, so now you want to show the same thing with the big matrix. So what is happening with the big matrix? So let's look at this trapezium, this trapezium here. It's called BLMJ here. So this trapezium does two things. It first of all acts on the past entries, these entries, but also it interferes because this part, this triangular matrix, this right edge matrix, which was working well and which acts on this lower part. So whatever its output is, it is passed into the, so the output of this trapezium is that plus whatever it does with this. So the trapezium has to act on this middle part, the BLXJ part, plus it also, plus the output of the triangle also interferes with whatever it is doing. So the whole proof essentially goes by showing that this trapezium, or in fact even the lower part of this trapezium, this rectangular part here, this almost is like a Dvoretzky matrix. So because these things are all very far from the diagonal, so their standard deviations are not so far from each other. It does look like a usual Gaussian random matrix. But what we want to, but it also is, but it's not just not the usual proof of the Dvoretzky theorem, because it also has to worry about the data that's coming from the right matrices. So there are two things. So it has to preserve the output of the triangular block. So it has to preserve the norm of the output of the triangular block. So this block is outputting some norm, which is dependent upon this. And whatever this thing does, it has to preserve that norm. Plus, it also has to preserve the norm of this part, which this triangle is not acting on, which only this trapezium is acting on. So just to repeat, so this trapezium itself acts on this part of the vector, right? So this is the input vector, it acts only on this part. The triangle acts on the more recent entries. Somehow inductively, let's say we have somehow showed that the triangle is working well. But now to prove it for the bigger matrix, on the larger, on the double the time scale, what you have to do is to do two things. One is to say that this trapezium, it has to do two things. One is acting on this part, so it has to show that it has to do something with it. So it has to show that the norm, that whatever star norm this thing has, this thing is appropriately scaling it up in the dagger norm. That is one part. Second part is that this triangle is doing something nice with this. So whatever the star norm on this part was, just the last part, this thing is producing some vector which has a large dagger norm compared to that. So square root of 2 to the j times that. This thing has to preserve both. So it has to, whatever its output is, its norm, the dagger norm, should be bigger than both the dagger norm of whatever is being output by this triangle, and it should also be bigger than the dagger norm, bigger than square root 2 to the j times the star norm of this part that it is acting on. So there are two things it has to preserve. So it has to preserve the output of the triangular block, and it has to preserve, in fact, increase the norm of its own input. And so that's one is to analyze that, and then do an epsilon net argument over all. So this is for one vector. This is for one particular x. Then you have to take a net of all these x's and show that. So you essentially want to show that this holds with high enough probability for each x that you can take the net and do the argument of the whole. Any questions about this? So okay. So not maybe just so yeah. So this. So as I said, this is sort of a starting approach to this problem. So So we sort of just looked at a random construction that works, and someone showed that it works. But more interesting would be to find more structured constructions with maybe less randomness, fewer random bits used. So in particular, one thing that we tried for a while but didn't make much progress is, I mean, this clearly has some kind of time invariant structure, right? So even here, the variances had this kind of, you notice that it only depends upon the distance to the diagonal. It's not like each I and j come, only the difference between I and j appears in the picture. So that's very much like a Toeplitz kind of structure. And one would wonder if instead of having this independent entries throughout the matrix, if the matrix itself could be made Toeplitz. That would both reduce randomness, make it more structured, so so that's easier to apply. But this is a problem also in the block setting. So they said like this idea of de-randomizing the construction, it's a non-trivial and open problem even in the block setting, not just in the triangular setting. The second thing, which is more algorithmic, is, so I just described the decoding as solving this problem, this argument over the range of a matrix. And that is a linear programming problem. But the way I describe it, at each time t, if you wanted to decode it, to solve the problem again from scratch. And analyzing if one can somehow do some warm start kind of a thing, where once you have solved this problem at time t, one would think that at time t plus 1, you should not need to just restart the whole process again. There should be an easier way to do this. This is something I haven't thought about much, but that's interesting. And this is the paper. Thanks.